Hello, everybody. Have a nice last day of our conference, and I have honor to introduce our last keynote speaker, Meelis Kull, who is a professor of artificial intelligence at the University of Tartu. He is the head of the Estonian Center of Excellence in Artificial Intelligence as well. His main research topics are machine learning, artificial intelligence, and data science, with a focus on uncertainty, quantification, and trustworthiness. But also, I know Meelis very well from years ago. Once we sang together in the jazz choir. Then, as I know him very well, I asked some questions to prepare today's keynote speak. I asked, is artificial intelligence who or what for you? If who, then he or she. And Meelis answered that when talking about artificial intelligence systems, I use both tema and see in Estonian. Tema is who, and see is what. It depends on the circumstances. Since English forces you to choose a gender, in Estonian language there is no gender, I don't say he or she, but it. And I also asked to name one thing or phenomenon in which the application of artificial intelligence is more harmful than beneficial. And Meelis said that an example of when artificial intelligence is harmful is when a person becomes stupid because they delegate thinking to artificial intelligence. So the floor is yours.
Thanks so much, Kadri, for the invitation, and it's an honor to be here and to talk about humans and AI. So I titled the talk Similarities, Differences, and Why It Matters. And it was something that I came up with already 3 months ago as a title, but as you see all the time around yourself, the world is moving so fast that it's really a challenge to put a title to such a talk so long in advance. But some topics that I would cover are here. I'm not a researcher in digital humanities, so it's not going to be a research talk, really. It's more about technology, how to think about it, how to understand the technology better. As I said, the title I had to give 3 months ago, and a lot has happened. So we've seen many new AI developments, and well, particularly in the text realm, but of course, audio, images, video, everything is changing fast with AI. I'm quite impressed every time a new model comes out. So even though my research is closely related to it, or maybe particularly because of that, who knows? But nevertheless, somehow I've seen that even though there are more and more capabilities, even these 3 months was still short enough that kind of the weaknesses that the models have in essence are very similar still. So I think my original title and the abstract serves me quite okay still. And then I thought deep research is one of the latest models, and what I did was to generate the full text of the keynote just from the title and abstract. The full text just in one go. And I could be giving this talk. I think if you wouldn't know me, maybe you wouldn't understand. Maybe getting a bit suspicious here and there, but it's quite amazing what these models can do these days. I chose not to use any of that text this time. Maybe next time, if I would get the chance. But this is still my talk, let's say. Now, we are starting to compare humans and AI here, partly. But comparing is something that has quite a few ethical dilemmas with it. So, I mean, even if we're comparing humans with humans, that can be a deeply problematic thing to do. Particularly if we just take one axis and put them somewhere, who's better than someone else. So there is clearly a risk of devaluing kind of the worst performing individual between the people we compare. And we really, I think, there need to appreciate that there are many different skills, and we should always think of several skills and always kind of appreciate that there is a possibility there are some skills we don't even are able to think about at this point. And so I think it's good to have an ethical bias that whoever is weaker in some comparison is almost surely stronger in an unknown skill. Why do I point this out? Because now that we then go to comparing with AI, we kind of face the same trouble. There is clearly a risk of devaluing. Well, maybe for the moment we can still get some good laughs at what AI is screwing up with, but it's getting more and more infrequent that we get that, and there is a risk that we actually take an opposite view. Well, maybe we don't want to do that, of course, but one way or another we might see that in some cases we are somehow forced to say that, well, AI is better in this, AI is better in that, and that list is getting longer and longer. So therefore, I think we should be careful when we're making comparisons. Why I'm making comparisons is not so much about humans, but more about AI. I just want to discuss what are the limitations of AI at the moment, and to understand why these limitations are there. So that's what the plan is for most of my talk here. I wanted to start from questions that sometimes, philosophical questions primarily, but that kind of create quite some discussion. Like, do AI systems really understand? Do they understand the meaning of the human concepts that we have? Or is it just a stochastic parrot, as it's often called, that really fakes understanding? I mean, we need to then define what understanding is. Of course, maybe we just have the intuitive notion there, but what do we really mean here by understanding? And my point then is that we should then be able to test understanding one way or another. I mean, how do we test understanding? Let's take a student instead. At an exam, maybe at the university, we want to test whether the student really genuinely understands or has just memorized everything, yeah? How do we do it? Well, we ask questions, and probably not the questions that were explicitly in the materials, but we test generalization, whether they can use that understanding somehow demonstrated on new tasks. And when the student doesn't understand, well, that we can reveal by coming up with tasks where the student fails. And I think that's the perspective that I would like to take with AI as well. Not so much to be concerned about whether understanding is something that is, well, can only be human, but rather take a more pragmatic view and see what understanding can help us do, and whether basically AI is able to use information in a way that we want to solve some tasks. Perhaps a bit similarly with creativity. Like I think 10 years ago, talking about computers and AI and creativity was like, hey, where is this creativity here? And many views were like, it's never going to happen that computers would be creative. Today, it's already quite different. I think there are still some disagreements, but I think many people are now taking the view that computers can be creative, even if they are maybe not fully yet, depending on the view. But another example about understanding. For example, take a person who was born blind congenitally and who talks about color. I mean, taking an assumption here, and I really want to try hard not to offend anyone's feelings with this, but basically whether color can be understood then. And I'm constantly amazed by how people who are blind can, first of all, achieve so much, but then also know a lot about things that they cannot directly perceive. So I think partly it's possible to take that as a comparison to think about AI systems. A large language model has never experienced anything in the sense of as humans do, because they don't have, and I said they, now the problem with the English is that it, and then you don't say it as the plural, right? So then I fall into saying they, and then, well, I might get into saying he or she soon, but we'll see. So it has no episodic memory. So anything new comes, well, it's only in the kind of workspace of an LLM, but LLM is not itself changing with that. Its state is changing, yes, but kind of the trained LLM is there fixed and is not changing, and in that sense, experiences are not piling up. And the training time, I wouldn't say that experience being an experience either. Or maybe we could and say it has experienced all the text that it had in the training set. Yeah, maybe we could think of that. But anyways, when kind of having a conversation with these kind of models, they can talk about experiencing in various ways, where it's hard to just from text, well, kind of test whether they can experience genuinely. But again, I would take a pragmatic view here. And what does that imply? What's the message then for AI usage? So something that we need to keep in mind when using AI is to try to stay within the boundaries of the knowledge of these models, or like boundaries of generalization, as I've called it here, so that we know that there are limitations that these models have, and if we push hard, we can currently make them fail. But for practical use, successful use of AI, we need to try to stay within the boundaries that are matching their skills, so to say. It's hard to know, though, where these boundaries are. And this is particularly one motivation for what most of my talk will be about. How to really understand better what the boundaries are of these models at the moment. I'm guessing that the backgrounds are very different here. So maybe just to get an understanding about the use of large language models in your work. So please raise your hands who have used large language model as a tool to work with large amounts of data, so that it's more than just I don't know, putting a query, one query in and seeing what comes out, but actually a larger scale analysis automatically AI system doing something. Let's say particularly large language model doing something. So can I get a raise of hands? Okay. Quite a few hands. Happy to see. I think on one hand, there is a risk that I'm not saying much new for you, but on the other hand, if I do, then maybe it makes more impact, so then you can use it more in your work. And then I'm hoping for the rest, I'm able to carry you also through with some useful insights, also for just very basic usage. Just some small queries here and there. Now, why these similarities and differences between humans and AI matter? I mean, when we're using AI as a tool, we need to know its limitations. Furthermore, I mean, if AI becomes more and more agentic, we can leave it to do long jobs, then it's more like a collaboration between humans and AI. And then we even more need to understand what AI can or cannot do at the current moment. So what are the ways to see what the similarities and differences are? I mean, first of all, what person or an agent or system knows or doesn't, or what kind of information it has, or he or she has. So another is skills. What can be done with this information? Reasoning, planning, creating. Speed can be massively different, both between AI systems and humans, and the resources. These days, AI really consumes huge resources, and that's a big problem. And why this all matters is that when we are arranging big, is it research project or some other big task with data, then deciding which task is better to do by human, by AI, how to organize the work, which human, which AI, all that is needing information about what are the strengths and weaknesses of each. And for an AI system, how can we get those? Well, we can learn about it from descriptions, but for an LLM, it's really hard to know in any other way than just playing around with it. So that's the primary way. I encourage everyone to play more with the AI system just to get to know what their capabilities are. But I'd also like to suggest that we should pay more attention to how exactly the models work, because that gives insights about the limitations as well. And that's what I'm now going to talk about next. So LLMs, large language models, I'm primarily taking examples from ChatGPT, OpenAI models, but not only. Currently, so one kind of a test that I've done several times already in the past 2 years is Estonian math high school exam tasks. So here are 12 tasks. So what I've done is just taken images of those, feed them into several AI systems. I mean, early systems couldn't really do it from image, but currently, if you use ChatGPT 4.0, give the task just as an image, it solves 10 out of those 12 correctly, 2 with mistakes. So it's kind of 90% of grade almost, maybe that can be achieved by the system. Other systems can, 01 I think was almost 100% already. So quite amazing. And it's not only math, there are many tasks that AI is really great at. And at the same time, there are really simple queries that fail. So, for example, asking the same system that solved those math tasks, write just the number of words with 4 letters in this sentence. So I thought of asking just write the number of words with 4 letters in this sentence, but I added this just to incentivize it to really answer only with a number. Well, if you do the counting, there are 4 words that have exactly 4 letters. And it doesn't take a PhD to solve this task, right? And out comes 3 instead of 4. The same system that solved all these math tasks. And it's just ridiculous, right? So I want today to really explain it in detail, why this happens. But this is wrong. Another example, output the word Mississippi with every 3rd letter omitted. Yeah. Again, very simple task. And the same model, again, fails with just dropping all the S's somehow and 1 I as well. Okay. Another example. Now I'm switching to a simpler model because this is a even simpler task. Just counting how many commas there are in this list. There are 9 and the model says 10. Okay, why? Another question, who is Friedebert Lutz? For those who are not familiar with Estonian literature, Friedebert Douglas and Oskar Lutz were well-known writers. So it's a combination name. It doesn't exist. I tried to find hard. Such a person didn't seem to exist. However, of course, the model hallucinates, as it's called, and tells me that it's he was an Estonian writer, and gives many details, partly then taking up Oskar Lutz's works, so I want to talk about how come these failures are there, why. So the primary reason is that LLMs are token predictors. So they just predict the next text. And I've put a small asterisk there. So I don't know if there are people who've been really following the news lately, then there was a diffusion-based model, Mercury Coder, by Inception Labs that actually doesn't predict tokens, but instead produces a random long piece of text, then starts to make small changes, gradually converges to the final text that is actually computer code that works. Very interesting. It's following the same strategies as have been used in stable diffusion in generating images and videos. But other than that, LLMs are token predictors, right? So what they do is first they split the given text into tokens, then start to predict. Now, what are tokens? Basically, these are just numbers, right? Each different piece of text is assigned a number. Already before training, it's a fixed numbering. There are currently these models, 4.0 has 200,000 different tokens. And the task of the AI system is take these numbers and predict what the next number is, the next token. I mean, when you look at it like that, well, it's quite magical, right? Well, that turns out that this corresponds to the word there, and then you feed that into the input again, and then you ask it to predict the next, and this is going to be 553, which is R, and then you feed that, also add that to the input, and then get the next prediction, and that's a space, and then you get 10, and then you get all the rest of the text until the model predicts the end of output token, right? I think probably most of you might know it, but I still want to cover some of these basic things about LLMs because they do reveal why the failures are there. Okay, so this is not exactly true what I just said, because what really happens is that instead of outputting this number, the model really outputs a probability distribution over all possible tokens. As I said, 200,000 tokens. and different probabilities. The highest probability turns out to be for the word there, and that's how this became be the output word. So it's a sample from this probability distribution, and of course, the most likely word is most likely going to be coming out, but not necessarily. So if you run model multiple times, you get different answers exactly because of this. So it might sample just another, sometimes then the less less probable output. And if we go further, so I've just sorted this now to reveal the 5 most likely output tokens. And then the next one, in this case, the model was very, very sure that the next word is R. How else would you continue the sentence starting with there? And then there is a space. And here there was more uncertainty because some of the tokens include space and already a word. So space 10, space 11, space 9, these are fully separate tokens. So it could have been predicting that. So it already was tempted to say 10 here. With 26% probability, we could have got a 10 here. And so on. So now we're getting to this next moment. And here, when space was already written, now it's a time to put a number. And here we can see that the model was pretty confident that the answer is 10, although the true answer is 9. So it not only just this time gave the wrong answer, but it was very certain that this 10 is correct. So why does this happen, or why is this hard for the model to do this? I mean, of course, we can see these numbers are... it's hard to decode information from these numbers, but that's what the model is trained to do. So it's not a problem for the model to take this number 82384 and get 4 commas decoded from it. That's the easy part. But what is then hard about this counting? We need to then think about how these models are, what the architecture of these models are, to understand why this is hard. So this is now, what I'm going to show is ChatGPT 3.5, so it's a very old model. But the reason why I'm showing this is because for this we really know what the architecture is. Of course, now there are latest models by DeepSeek, for example, from China, that is also known. But let's take this a bit simpler, older model. So in goes a list of tokens. And what is going to happen to those? So first of all, there are certain kind of computational blocks. So some computation is applied on them. And that is happening in parallel. So in this particular architecture, there are so-called 96 heads. And I'm kind of simplifying some of the things, but just to explain the main point. So 96 heads that do the computation. So it's not too simple, not too hard either. It's somehow aggregating and doing something, getting out some numbers. And then there is a next layer of computation. And this is now, once the first layer has finished, second layer starts, and so on, so forth. So there is some computation in parallel, but then some sequential. And what really matters is that the number of sequential steps is relatively limited. So in this architecture, there are 96 layers, or kind of groups. I mean, each layer has kind of groups of some sequential steps as well, but primarily 96 layers. And out from there comes eventually a probability distribution that we saw. But the 96 is not so much. I mean, because these layers need to do all kinds of things, decoding information from these token numbers and understand what the task was even, kind of pick and find the right kinds of information from this input and then start to do things with it and then get to the answer. So it's loads of things that need to happen. So this 96 is not so much. And it is a fixed amount of computation. And that fixed amount gets, or almost fixed amount, it also depends on the length of the context, but it has to happen every time the next token is produced. And what this, here is an example of an architecture of a very, very, very small model, nano GPT, only 85,000 parameters. But why I'm showing it's possible to go on that website and see like zoom in and see every single parameter in the model. So really to get a feeling about what the model is like. So because of this, we can start to think of how and why LLMs make errors. So when does an LLM make an error? Well, if it cannot predict the next token. That's, of course, a trivial answer, not telling us much, perhaps, but then we can ask why. Why couldn't it make a good prediction there? One thing is that maybe it just didn't have information. It was asked about a fact that is not known to the model, wasn't in the training set, or maybe in the training set it was very few times, and it just didn't fit into the brain of the model. The models are huge. We're talking about hundreds of billions, maybe trillions of parameters, but the training set, the whole internet, was so much bigger that it's clear that we just can't possibly fit all information in there. So models just need to prioritize, and they prioritize by frequency. So if you think of whether a model would know the answer or not, first think of how many times was this fact mentioned on the internet. Yeah, I think that's a good proxy for that, and to assess what are the chances. Another, and now that's what I really want to focus on, is the limited reasoning steps. As I said, the architecture has fixed number of steps each time when a prediction for the next token is made. So that means that can be a limitation. So if the prediction task is so hard that you cannot compute it with this architecture with one single go, then you can get a wrong prediction. And then from there on, because every next token depends on the previous, once you make an error, things go bad. So that's, or typically go bad. Not always. There are ways maybe the text could self-correct it later, but like the next text could say, okay, sorry, I realized it was wrong. Sometimes this can happen, but most of the times models stick to what they have already said. And the third one, well, maybe just the learning sometimes wasn't kind of correctly recording information, or maybe the sources were bad. There are other reasons kind of that could be there, but these A and B, I think, are really important reasons. C, of course, also, but okay. Now, how to deal with this? The same question that I had earlier, write just the number of words with 4 letters in this sentence. I, in brackets, say step by step. And that's a hint for the model to answer not just by a single number, but to work on this text. So now it starts to give us a long text which step by step gets to the answer. And this is now correct by the same model that made a mistake. So why? Well, if we now look at what were the challenges to get to the right answer. So when it was outputting this just at that step 2, it had to find the first 4-letter word in the text. And it's a lot easier task than just spitting out the answer immediately. So for that, this may be whatever the fixed number of steps in this architecture are, this was enough for the model to be able to do it correctly, at least this time. And the next task is then to say with it now needs to find the first 4-letter word that is after this previous one. And that's also a bit easier task than solving the whole thing. So we see a sequence of a bit easier tasks, and that's the key to simplify the work or the task for the model. So spread the complexity, prediction complexity across many tokens, rather to have one token where all the kind of complexity immediately, everything needs to be solved when predicting this token. Like the answer is, and that token is super hard to predict because you at one go need to immediately solve the task. But if you can split it this way, that's a lot easier. And so this last moment is to just count the number of words in step 2. So we made it easier for the model. We can now actually turn to even simpler model. This is 4.0 mini, and this can even solve it. It used its own strategy even to list all the words of the sentence to be able to solve the task correctly. Well, in the training process, probably the model also realized that because it's a smaller model, it needs to do longer kind of sequences of argumentation to get it right. Even simpler tasks for each token. Now, the newest models are reasoning models. These are now since September last year. 01 is one example of those. What this model does is first thinks and then says. So it thinks before saying, which is great. 5 seconds thinking got it to the right answer. It's not revealing its full thinking process here. OpenAI chose to only show bits and pieces of it, but something we see, and then we get the answer. In comparison now, DeepSeek, which is the Chinese model that was published in January, it's open weights, so everyone can download, and if you have 8 GPUs server to run it, or something like that, then you can try. Or you can just use some cloud-based services for that. But this model, when you use R1, which is reasoning, it actually thinks 25 seconds on this simple task just to count. So what the hell is it doing all that time? So it okay, let's see. And this what is good about this model is it shows you all the reasoning it has, all the thoughts that go through its mind. You can all see that. So okay, so it's fun to read what it's thinking. But it's so long that we don't have time to see it all. So it says, yeah, okay, let's see. The user wants me to count, let me list each word. And then, but let me check again to make sure I didn't miss any. Again, going through, or let me count again. Perhaps I miscounted a word. So yes, 4-letter words, therefore the answer should be 4. Okay, finally got it there. So 25 seconds spent on it, but well, just to be sure, humans also sometimes want to be really sure. We really double check things many times. We know our limitations, but there is an easier way to make sure that things work well, in this example at least. So in brackets I've said use code. For the same sentence asking to count. And the simple 4.0 mini model, the mini model gets it right. Just putting out the right number, and there is a small brackets to click, and you can see that it's produced code. Why is this better? Well, because predicting what is the next piece of code is an easier task than immediately predicting the answer 4. Because answer 4, well, you need to do a lot of counting, but predicting the next piece of code typically is a lot. I mean, the hardness is kind of spread out across the whole code, and then somehow every small piece is a bit easier. At least to the model. Maybe not for us, or hard to say, but for the models, this is an easier task. So this is really, all this is to say that step-by-step reasoning is really important. And why is that basically we want to avoid hard-to-predict tokens. With that, we also win more time to think, because as I said, for each token, there is a constant depth of the architecture. But if you have more tokens, that means in total, overall, you do more computation. And so maybe you can think of it as kind of winning time to think. And using more working space. Also, what intermediate results you produce, they are in your output, you can use them. So, that's why step-by-step reasoning is really useful. But relating to that, supervised fine-tuning and reinforcement learning from human feedback are important steps in training those models. So first, there is this huge pre-training just to predict the next token. But then there are these supervised fine-tuning, reinforcement learning from human feedback steps. And these are ways to guide models towards doing step-by-step strategies that humans like. Or first of all, human-like, but also that what humans appreciate when they see in the output. And this really improves the usage of the model experience. But then there are reasoning models, as I said, and these are trained with end-to-end reinforcement learning. So there is, at least as far as we know, I mean, for O1, we don't exactly know what is happening there, but generally, quite sure that this is the way. So basically saying that we want that answer, figure out yourself a way to, what is the best strategy to get to that answer. And it's kind of it's partly trial and error related. I mean, there is still gradient-based learning in there, but these strategies are not necessarily what humans find the best, most effective step-by-step strategies, but this is what AI finds for itself what works. And that's making it really powerful. It's a bit similar to how computers train to play chess and Go these days. I mean, earlier they were also trained from human information. That's related a bit to this SFT or RHLF, not exactly, but analogous. But now, really, the strongest models come from end-to-end reinforcement learning. Okay, so, but I showed you more problems early on, so let me come back to some of the other problems. So there was this Mississippi example. So what is happening here? Is this a similar reason why it fails? And in a way, well, yes and no. But I mean, what's really the problem is I mean, we see Mississippi as a sequence of words, but the model sees it as two numbers. It's only two tokens that make up Mississippi. And so for it, the task is to take those two numbers and figure out what would be the perhaps also two or whatever, how many tokens there are in this correct output, but figure out what the number should be. And without it really needs to more work than us, we immediately see and can work with our visual workspace, whereas the model needs to work only with numbers and create for itself this internal workspace, but it has only fixed number of layers and it just fails in that. But of course, again, once I say use code in brackets, things work because it can now write up code that does it for it. Now I mean, of course, writing that code, it also needs to somewhere write Mississippi, but only in its original form. And so basically, needs to copy over from input to output, so that's a lot easier to task again. And this was mini. This was so the model that originally failed on this was the bigger model 4.0, and even the mini model can do it once you ask it to use code. Now to these hallucinations. Friedebert Lutz. So what's happening here? Why is it thinking that Friedebert Lutz was an Estonian writer? So what I did was to just look into the numbers. So with OpenAI API, you can get access to these 5 most highest probabilities in the whole vector. You don't get the full vector, but you get 5 highest ones. And if you're playing around with the models, I suggest you to sometimes to look at those. So you can see that the model wants really to start the answer by saying the name. 99% and more probability. But then once it has copied the name, what comes after? And then it's with 67% probability, it thinks it's a bracket should start, probably thinking of to put birth date, and 32% probability to put was. So if we go on, birth year, interestingly, it's very, very sure, super sure that it's 1880s. Just from the name. So I think it clearly is already thinking about, probably about Friedebert Douglas, but hard to say. Actually, both were born, Oskar Lutz as well, in 1880s. Another question I tried a bit to change. So Friedebert Hamsun instead. Turns out also Estonian writer according to the model. But then realizing, suggesting that Friedebert Hamsun was translating Knut Hamsun's work. So what's going on here? So to me it seems, okay, and then I looked at the particular prediction when it started to say Estonian. And it's extremely sure that Friedebert Hamsun was Estonian, which is also a bit surprising perhaps. But I think I would attribute to the Friedebert being really a very unusual name and only particularly in Estonia used. I don't know any Friedeberts other than Friedebert Douglas, but maybe that's me. So it really thinks this person was Estonian. And not maybe then, not paying enough attention maybe to Hamsun as the surname. But when I asked Kalle Hamsun, then Kalle Hamsun, no problem, the model says it's not a widely known name. Which is interesting because it's somehow this Friedebert that really made the model think, oh, this must be an Estonian writer. Okay, but looking into the predictions here, Kalle Hamsun is, and then what is the next token predictions? It thinks is already suggesting maybe with 61% probability it could have started to hallucinate something. Is but it somehow in this particular case took the probability 37 to predict not instead. So just by sampling, throw of dice this time came out to this word not. But when I triggered the same model again on the same question, even this is ended with the model appreciating that this person doesn't appear to refer to any widely recognized figure, which is also great. So really, this time it didn't mess up. So somehow there are certain patterns like Friedebert and Estonia, certain patterns that really trigger the model to be quite sure about things. And when you don't have those strong patterns, it's more likely that the model can really say that it doesn't know. This seems to be one possible explanation. People study this a lot further. I'm not closely following this literature, but it's interesting to think about why this all happens, how the whole training process matters. In general, the models are getting less hallucinating typically these days because the training processes are using certain tricks to reduce this. Also, in the training set, I think there are some texts put intentionally in that are answers like I don't know for various cases. Okay, one trick that can be done with those models when using them, at least through APIs, is that you can lower this temperature. That's one parameter that can reduce randomness. So it's a particular formula how the probability distribution over tokens is changed, and basically whatever the distribution is, it's made more. So the bigger probabilities are pushed up, and the smaller ones are pushed down, so that it gets closer and closer to the probability distribution where there is one particular token getting probability 1. So if you reduce the temperature all the way to 0, you get a certain answer, always whatever used to be the most likely in the original distribution. So overall, about hallucinations, so model predicts just the likely continuation of the text. That's what they are trained to do. But the thing is that during training, these hallucinations can have lower loss than frequently saying, I don't know. So therefore, somehow the model has been incentivized to hallucinate. And people try to fix it in the training processes these days, but it's still an open problem, I would say. So just an example, like I'm also head of the Estonian Center of Excellence in AI, and particularly my group works in uncertainty. I mean, we have 13 research groups, both in University of Tartu, Tallinn University of Technology, and also a company Cybernetica. But one project in the center is where my group collaborates with the machine translation groups to include this kind of uncertainty information to translation outputs, because otherwise typically the model outputs just one translation, but you might want to get more information. Here the alignment of the lines is a bit messed up. I think the font's changed, but the point is to highlight words that the model is not sure about, and that can be useful information for whatever the translation is going to be used for downstream. Now getting back to this view that I already presented to you, so there are humans and AI that have different information, different skills, different speed and resources. But I was focusing really on text models. So I just wanted to say a bit also more broadly about other AI systems, and particularly classical machine learning systems that are, well, maybe not neural networks, or if they are neural networks, then it's something simple, not a big transformer-based huge model. And when thinking about what these models can do, I really found it useful to read this book. I would recommend Daniel Kahneman's Thinking Fast and Slow. So what really briefly the message is that humans have kind of two ways to think, fast and slow, where fast is kind of automatic and intuitive and effortless. And there are like examples like when you recognize someone's face, it's really automatic. You don't need to make an effort to do that, at least most of the time. But then there is also thinking slow. That is the hard thinking, when slow, deliberate, analytical, effortful, when solving puzzles, making decisions, hard decisions, all of that. And why this was useful for me was that I saw this kind of analogy with how machine learning systems, the classical ones, operated and do operate. So I would say the classical systems are really typically system one. And it's almost like we could put it also the other way, that whenever you have system one problem, you can solve it with classical machine learning systems as long as you have enough data. Of course, this might need a lot of training data, but it's a good heuristic generally. So if it's a simple task, doesn't require, recognizing faces is not simple if you start to code it with a computer, but for humans it's simple. But then if you have enough data, you can get AI to work with a classical machine learning system, typically, I would say. But this thinking slow was something that maybe a few years ago I would have said, well, computers are typically not doing it, or if they are doing it, then it's more like chess playing kind of a way, like just really high throughput, looking through all possibilities in some space and solving it that way, but not in the human way. But now what we're seeing is that these get combined with the transformer-based models, with diffusion models, so we get both. But then there are still things that don't work as well as I showed you. So there are challenges, but we are now getting system 1 and 2 both. With that, I would like to get towards the last points. First, about key directions and challenges in AI. So where I see AI is heading towards at the moment, I mean, it's not kind of going to be an exhausting and full picture of everything, but just some highlights, I would say. So improving reliability is what many researchers work on these days. Reducing hallucinations is just one example of that. But then we are seeing that more and more there's kind of convergence. So instead of building many dedicated AI systems for different tasks, we are seeing more and more AI systems that bring together everything and all modalities, text, images, audio, and so on. Now, one thing is bringing them together, but another is how these are getting used. And I think this is still a bit limited. So particularly what I'm not seeing very much yet is multimodal workspaces. So what do I mean by that? Like if we think about how an LLM is reasoning and thinking, it's through its output in a way. I mean, it's whenever it comes up with something new, it puts it into the output text, and then it can be reused, and then the thoughts that it had with it can be reused in the follow-up. But it needs to go through that explicit textual representation as well. But it's what the models typically are not doing yet is thinking, for example, visually. I mean, they can produce images, yes, they can produce videos, but the same kind of thinking as we humans have, like imagining something, maybe it's even an abstract concepts and whatever. Well, some of us think more visually than others, but like thinking of a timeline, I'm immediately drawing mentally a line and then maybe putting some events here and there, and then I can more effectively work with that compared to if I would need to write out everything in text. And I think that is one direction that we will probably see very soon, developments where models can start to, during their thinking processes, draw things. We're not seeing that much yet. Another thing that is special in humans is continuous learning. And in case of models, we separate currently training and inference or test time. And during inference, no explicit learning is happening. Well, there is something that is called in-context learning, but that's very, very limited. And that needs to work then with this typically textual workspace and it can do a bit in its output. You can see a model finding out, when solving a task, writing out things about it in its output and then getting to use that. But it's a very limited way of learning. And I think humans are a lot more powerful than in that, and that's what we are starting soon to see more in AI systems also. And then, of course, all of the resource problems. Too much energy spent, huge hardware, like compute centers, all of that, that is so hard on our planet at the moment. So there is a lot of work to try to make that better. But you make it more efficient, and then they build more and more. So it's a huge challenge. What is also interesting direction is currently the models. When you use GPT-4o, you always use the same amount of compute when it's operating. But what could be the case is when task is harder, it kind of gets to use more resources. When the task is simple, it kind of gets away with, I don't know, GPT-4o mini kind of a model. And it would do it dynamically. I think there are already first attempts in this. I think it was Claude's models, recent ones had something in that, but I'm not sure, I haven't tried. And then there is a huge field and direction about how to make things more explainable, fair, aligned, safe, secure, how to control this whole AI systems, bias, all kinds of topics. So there are many risks that we see, and a lot of work going on there. Now, so this is how I see the future at the moment, but I'd also like to briefly emphasize 2 points here. Like first, this explainability that I mentioned on the previous slide. We need explanations as humans. We're not happy with just an answer. So why is that? And what is the kind of explanation that we need? What is the best possible explanation? I mean, I'm a mathematician, at least my soul is, perhaps. So a well-written mathematical proof, that's what the best explanation is, yeah? Of course, not many would agree, but the thing is that it's harder to predict, so harder to explain than to predict. I mean, models, machine learning models have been good at prediction already for a while, but really struggle even more and more in a way to understand what they're doing and why this kind of a prediction and why not something else. So on one hand, it's going worse. And one reason is that, I mean, we understand whether we typically understand when we are hallucinating. I mean, not always perhaps, but most of us, most of the time, do understand. And the reason we do is that if something comes from memory, we have a kind of internally different, feeling about it. We understand that this is something that came from memory, rather than us inventing it. Yeah, models have everything coming through the same directional forward architecture, and it's all mixed up. It's very homogeneous architecture that transformers have, and it just comes all from the same direction. And so income perception, but then at the same time, the weights, pre-trained weights, insert all kinds of information into the process. So memory is also in the same place almost. And the reasoning is also going on so if there is an algorithm being applied, it's also in the same processing. So it's all mixed up. And therefore, it's maybe even a lot too much to ask from a model that it would understand when it's hallucinating. But I would say that this is why explanations is super hard to get. We are starting to dig into the big neural networks as well to highlight some role of a particular neuron, but that's not going to solve the full explainability issue. So I think And first of all, why do we need explanations? We don't trust fully the models. If we would, maybe not so much of an issue, but then still we want information as well. Explanation also is more information, and we just want to learn. We don't want to delegate all the thinking to the models. We want to think ourselves, and for that we need to develop and learn. So there are many reasons for getting explanations, but the problem is that there is a trade-off also between accurate explanations or faithful explanations and those that would be understandable to us. So want to make it more understandable? Well, simplify more, but then it's not faithful to the actual reasons. Now, the direction I see being the main hope for the future is that AI gets better in giving post hoc, like after it has figured out the result, giving better post hoc explanations and then constructing proofs, kind of. Well, maybe in that process, it's also double checking maybe what it's figured out earlier more intuitively, but then it goes through a bit similar as a human. First, maybe you get an answer and then you start to check and realize how exactly you got to that answer. Even mathematicians, they don't typically write the proof like that, but they do things and then they somehow come to ideas and then they construct eventually the proof. So I think it's going to be similar, and not in only mathematical tasks, but all across the board. That we're getting post hoc explanations and these are getting better, and we can maybe push, as mathematicians, I would like these to be more logical and to fight against the post-truth era with that we can construct better logical, solid reasoning trajectories. But explaining the full computation is unrealistic. So I think it's really the post hoc explanations that we are going to have primarily. And with that, the role of humans is changing with developments of AI. On one hand, every individual can do more, which is great. That brings a need also to. And I'm not in this slide talking about all the risks. There are so many risks. But we need skills as humans to give orders to AI systems, because we can. There are more and more they can do, but all we need to do is to figure out what do we really want. And we can easily make a stupid mistake from a fairy tale that we want everything that we touch to become gold. And that's what will happen with everything. But maybe that's not what we actually wanted. So we really want to understand how to what we really want, and it's about giving orders, and that's a skill that needs to be developed. Prompt engineering as a field has been kind of relating to this, but I think it's less and less important of how exactly we construct the prompt, and more important that we really have all the information there, really understand what we want and be able to express it. Also, leadership skills, I think, is something that we need to develop in our youngsters, because that's becoming increasingly valuable. And then creativity. All authors, artists, writers, all of that. What's the future there? I think it's not only the creation itself. It's about making the choices that come with it that really have impact for the future of humankind. So for that reason, I really believe in the also the possibility of positive future for all of the authors that might be concerned that AI would replace humans in this creation processes. But we are the ones that want and should make choices in this. We as humans. Finally, some suggested materials. I already mentioned Thinking Fast and Slow. This brief history of intelligence is a really nice, quite thick book comparing how brain developed and how AI developments are kind of matching different stages in the evolutionary development of our brain, and what is still missing, and kind of helping to understand how we think also at the same time. I mentioned Thinking Fast and Slow, but then there is a blog, sorry, not blog, but a video by Andrei Karpathy, video lecture, basically 3.5 hours. And that has many aspects that I already covered in my talk, but a lot more extended and really insightful for people who work with large language models. And the fourth suggestion is the LLMs themselves. I think really, I mean, deep research, if you didn't try, you should. Just asking about things and discussing, and I see that a lot happening in my research now with my PhD students using both deep research and other LLMs to be more productive, to get not get stuck as easily, and get progress in thinking processes and learning going on more effectively. So that's it. So I covered these kind of grounds: understanding and why it matters, understanding LLMs, and what are the failure modes, why step-by-step reasoning is important, and some of the future. Thank you.
Really, thank you very much. It was like a whirlpool for me, because I knew a lot of before, but how you connected all this knowledge is how it explains the deep research in this field to our humanities. So, but there is also time for discussion, questions, comments. You're welcome.
Okay, thank you. Thank you for a very fascinating tour. My name is Mats Friedland. I'm from the University of Gothenburg, and I want to sort of pick your brain a little bit about one of the last things you said about the changing role of humans, and then you emphasize sort of increasing leadership. And first, I wonder why you mentioned that in this context. First of all, that is something you should say, regardless of AI or not. I mean, you should foster leadership skills. Yeah, you could say that all through history, of course, history, and today. So I wonder why you emphasize that in connection with AI. Is that because also leadership, when we normally think about it, is about leading other humans. But I'm guessing that's not exactly what you mean, or?
Yes. Thanks for a question and pointing this out. That I did mean indeed leadership of AI systems more in this context, more than leadership of humans, because I see so many ways that that kind of leading a herd of AI systems or AI agents is similar to how we work with humans. Of course. Let's say leading a group of I don't know, research group or a company or an organization, there are so many things that we need to pay attention to because we're working with humans particularly. But there are also other things like just organizing who does what, when, what are the instructions, who needs what information. All of that is very similar to how you kind of orchestrate AI systems to do stuff. You need to pay attention to what kind of information can I give to the AI system, what kind of instructions should I give, and that's very similar in various ways how human leaders do this orchestration.
Thank you for your fascinating talk, and I have so many questions, but for instance, why Mississippi 2 tokens and not 1? But that's a unnecessary detail. I was wondering, do you think if and how much there is a way to sort of like backtrack and say, okay, we made some mistakes and we have to redo them or rethink them, especially considering this kind of multimodal AI discussions, because a lot of the current image generation is based on living artists' actual visuals, and all of those training models are not taking account, or have so far not taking into account, the actual copyright issues, the ideas that people's voices and faces belong to them. And to a certain extent, I'm a bit afraid of like, have we gone too far? Can we stop and backtrack and say like, oops, that went a bit wrong direction. We have to redo some of these things. And do you think that's possible or not?
Thanks so much for the inspiring question. You mentioned backtracking. I first thought of those monkeys shouldn't have come down the trees, but okay, we did. So now we're here. The second connection to backtracking was just the AI technological question, like how the AI system can, rather than just produce text one directionally forward, can it kind of backtrack and make revisions to its own processes. And I think, yeah, that is certainly being also considered. In a way, reasoning models can, well, they produce something internally, and then the final output is a separate thing. So, but okay, but then your really final most important point, I guess, is about the authors and the way AI systems use these. They're really hardworking authors and the results of those with copyright. Why is there a way that the model generations would start to? I mean, first, should they know about these works? My view is yes. That I mean, if we allow other humans to look at these works, maybe we should not forbid AI systems also to look at those. But what should be done is that the systems would appreciate this authorship and explicitly avoid getting too close to generating based on directly someone else's work. I mean, similarly as human authors, we try to explicitly avoid copying someone because that someone is going to be annoyed. So we should make somehow the AI systems to be more aware of what the sources of inspiration are, and kind of the ways that all this information would be used is less direct and more just very broad inspiration. So we, of course, artists take a lot of inspiration from other artists' works, but that shouldn't be as explicit and direct as in the case it is currently with generative AI. I would hope that is one part of the solution, but the other part of the solution must be that human authors just get new ways of getting compensated also for some of the market going to use AI systems. We should incentivize everyone to use human authored works more, but inevitably some of the market goes to AI generated work, and we don't want to lose the culture during that. So we need states to come in and support culture.